Yeah, you are live now.
Good afternoon and a very warm welcome to one and all present. Hope you are having a great day and congratulations on your JEE Advanced result. I congratulate you once again. The 2-year JEE preparation has taken perseverance, and with this Virtual Education Conclave by Techfest IIT Bombay, we wish to bring to you the information tools to satisfactorily conclude the journey by choosing a technical stream and college. So keep your questions handy. We'll be starting right now. And you can put your questions even during the talk. We'll take it after Sir finishes speaking. So all right, let's get started without any ado. Hello everyone, I am Aditya Agrawal and I welcome you to the first edition of Virtual Education Conclave by Techfest IIT Bombay. Techfest is the Asia's largest science technical festival, and before you all become engineering students getting to attend it in person, let's have a look at the after movie now. introduce you the esteemed speaker for the session, Professor Shantanu Roy. He's a professor of Chemical Engineering Department, as well as a Dean of Academics at IIT Delhi. Welcome, sir, and thank you for being part of our Ed-Conclave. Handing over to you now.
Yeah, thank you, Adit. Wonderful to be here. In fact, one is always reminded of such interesting times when we spend as students, and I'm glad that you've invited all your prospective candidates who've just cleared JEE Advanced. And so, first of all, a great word of congratulations to everybody. I think it's great that you've been able to clear this, possibly one of the toughest exams that we know of. I guess with this quota factory and so on, this is now the flavor of the season in some sense. So yeah, congratulations again. Great that you're here, and great to talk to you and speak to you through this online forum. And thanks again to the Techfest team for inviting me for this. I was told that I should be speaking on what career prospects lie ahead as chemical engineers. I don't know if I'm kind of qualified to comment on that, but nevertheless, let me try to kind of walk you through some of the background. One of the things about learning about any profession is to look a little bit at the history of that profession. And I can tell you that maybe now, I feel old already, some 30 odd years ago, I was at the same predicament. I was wanting to figure out what was chemical engineering about, how was it different from chemistry, which is of course the default question that everybody has, and whether chemical engineering is going to give me options to get into other disciplines, or am I stuck with stirring viscous solutions of polymers in a beaker and smelly chemicals all around you. I had all these questions, and I don't know if I have all the answers today, but nevertheless, these things were bothering me, and I'm sure it bothers many students. It's really the fear of the unknown. And I know that the environment has changed quite a bit in these last 25, 30 years. I think there is a lot more awareness. Internet was not there when we started as BTech students. And in fact, it came on during our tenure as BTech students. That was one big thing that happened. But having said that, so how has the world changed, and how are what to expect in a career in chemical engineering? And for obvious reasons, it is not that you're likely to stick to what you start studying here. In all probability, even if you pursue a career in technology, you're likely to move into many different things as technology evolves, right? So, I can tell you that some of the things we learned as BTech students are not what is taught in the BTech programs, definitely in the IITs. I can speak definitely for IIT Bombay or IIT Delhi or IIT Kanpur. The curriculum has changed significantly. But I think in the next curriculum, I know that there's some change in IIT Bombay happening. We are putting together a review of the curriculum like we do every 10 years, and I'm sure new things are going to come in. And by the time you guys become professionals, I think there will be a lot of new changes. So what I'm going to try and do in the next half an hour or so is walk you a little bit through the history of how this profession of chemical engineering came along. It's interesting how it got evolved, and it's also interesting that it was never intended to be separate in discipline of engineering. But it did turn out to be one of the more defining disciplines, at least of the 20th century. If you think about it, the wealth that you see around in the world today, mainly, of course, with the Western countries, somewhat, some with Australia and Japan, but most of it is with Western Europe and North America, is really built around an economy which we call the hydrocarbon economy. Right, and that big change happened in the 1920s, post First World War, between the First and Second World War, and then of course post Second World War. So the whole world was built around this hydrocarbon economy, and now we as a world are looking at the problems that we've ended up creating. Right, so end of this month, you might be aware that there is going to be this COP26 meeting in Glasgow, which is basically targeted at decarbonizing the world economy. And I can tell you that both in carbonizing the world economy and potentially decarbonizing the world economy, chemical engineers had a very, very significant role. So we both created the problem and we are also part of the solution. Modern day wealth and this free market economics that we all kind of revel with now, and a lot of IITians have made their big careers out of this, is really built on the hydrocarbon economy. And I think it's important to appreciate that how the profession came along. So what I'm going to do is I'm going to share some slides and maybe spend another half an hour or so discussing some of those things. I will not go through every slide critically, but I'm going to just kind of flip through them to kind of give you a feel of where things are. And so let's see if this goes through. So are my slides visible?
Yes, sir, it is visible.
Okay, great. So I'm going to switch off my camera to save some bandwidth, and I'm going to project my slides. And let me see. I'm going to stop my video. I'm audible, right? I'm clearly audible.
Yes, sir, perfectly audible.
Okay, good. So let me go to slideshow mode. Yeah, so I think what I'm going to try and address, hopefully for the benefit of prospective students, but frankly for benefit of everybody, including myself. So I think preparing this presentation for this little seminar was instructive for me as well. Oftentimes we keep doing things without realizing what we are really doing. And so I wanted to ask this question: what is chemical engineering about? Is it only decided by your JEE rank, or is there a professional gravity to the whole thing? And I think I'm going to try and address some of these questions. Not that I don't claim this to be a final word in the profession, but I'm going to try and tell you where this profession came along, where we are, and where do you think this is going to be. I'm going to do a little bit of crystal ball gazing towards the end, give you an idea of what are the main issues that are going to happen in the 21st century. So by the time students who are joining chemical engineering, become professionals, you'll end up becoming professionals in different fields. Not necessarily that everybody's going to do chemical engineering. You might get into other kind of streams. You might get into other kinds of research. You might get into management, finance, all kinds of things. The fact is that we need to understand that knowledge and human endeavor is not branch wise. It is not like choosing a branch after JEE. The real world is a lot more complex, and there are no barriers really. So you find a lot of chemical engineers working in a company like Intel, for instance, which is core to manufacturing silicon wafers. It's core to the entire computer revolution. It's really a chemical engineering device. The Pentium processor is really coming out of work done on crystallography and making silicon wafers and chemical vapor deposition. These are techniques to make wafers. And what I want you to note is that a company does its work based on what it needs, not what your JEE rank was or which profession, which discipline you actually studied. They'll get everybody who has a certain set of skills. So having said that, to kind of give you a little brief of what is this chemical engineering about, how does historically, what are the main things that happened? And if I might kind of use my, let's say, a spotlight here. I put together a lot of pictures here, and this is not meant to be any kind of encyclopedic thing, but what I do want you to appreciate is that the thought of transforming chemicals at a large scale is something which has been with mankind for a pretty long time. And one of the questions I saw in the chat box while Adit was presenting is, how different is it from chemistry? Well, I might say it is very close to chemistry from one angle, but from another angle, it is very far. Most of chemical engineering is actually a lot of physics, a lot of mathematics, and if I might add, a small amount of chemistry. Right? It is quite incorrect to think that chemical engineering is really amplification of chemistry. It is not really that. However, chemistry does form a very core part of chemical engineering. But please note that chemistry forms a very close part of all engineering, with possibly exception of computer science. Every engineering is really built on chemistry, right? So electrical engineering, electronics, particularly mechanical engineering, they're all built on chemistry. So for instance, if you look at this collage, what I have here is what is numbered 1 is a cartoon of Macbeth's three witches. If you read Shakespeare Macbeth, it opens with a cauldron and 3 witches. So that's a little cartoon of that. The number 2 image is actually from a Indian chemist by the name of Varaha Mihira, who actually tried to do a lot of work in metallurgy many centuries ago. And in fact, he made some innovations. The third snap here is from Chinese invention of paper, which happened around 1,000 years back. This is a chemical engineering product. In fact, most paper companies like ITC hire chemical engineers in big numbers. Number 4 is really about what was in Middle Europe. Europe in the Middle Ages referred to as alchemy, the idea of transmuting elements. And this was a big thing. It was, of course, a pseudoscience. It never worked. But I have to tell you that a lot of processes that are used today in the engineering discipline are actually inherited from the times of alchemy in the 12th, 13th, 14th century. Number 5 here shows a coal furnace. This is the core of all power that is getting generated, at least to a large extent, definitely in our country, but actually large parts of the world. You might be aware of, been following the news over the last couple of weeks. There's this whole power crisis that is happening in China, and India was pretty close. And I think we still are perhaps not out of the woods. This is what a furnace looks like. There's coal and there is very high temperatures. And to understand this, you need to understand chemical engineering really. But I will not get into details. But I just want you to know that this is an area where chemical engineers have to do a lot of work. Number 6 is what is called an oil refinery, right? So this is a view of an oil refinery, which you will see is pretty clean, right? I mean, if you look at it, you're taking dirty fluid like petroleum, but it ends up creating a pretty interesting look to the whole thing. Number 7 is actually a internal combustion engine. So if you open up your vehicle, your car or your bus or whatever, you're going to see something here, which is actually a chemical reactor. It produces energy for your vehicle, for your car. And this is, again, a very important part of your chemical engineering process. 8 is another view of a refinery. And the 9, 10, 11, 12 are basically things which are going to come in the future. And I will talk more about it as I go forward. What I do want you to appreciate is that, so I don't know who's doing the scribbles. I definitely am not. So I don't know, this needs to get removed. Yeah, so if you look at...
So you are sharing the screen. So over there, a bar must be coming. You could go onto that and tap the 3 dots, and then you could disable the annotations.
Yeah, I think so. So
a floating bar of Zoom must be coming on.
I did that. Yeah, thank you.
Yeah, sir.
Thanks, yeah, so I looked at, I mean, just for everybody's information, not that I'm trying to propagate anything, but if you look at Wikipedia and look at the Fortune 500 list from last year, just a minute. Yeah. So if you look at the Wikipedia list, I took up the top 10 companies from the global Fortune 500. And interesting to note that all the ones which are marked in red arrows, these are companies which chemical engineers are the dominant employees. There are, of course, any company has people from different disciplines of engineering, but chemical engineers are the dominant employees in all these companies like Sinopec Group, State Grid, China National Petroleum, Royal Dutch Shell, Saudi Aramco, and BP. These are, of course, in the petroleum sector and energy sector. Nothing really beats that. This is what is the 2020 figures. And a couple of other companies, namely two auto companies, Volkswagen and Toyota Motors. Of course, these are largely mechanical engineering companies, but they also employ a good number of chemical engineers. Again, I'm not trying to propagate anything. I'm just trying to tell you facts as they are. If I looked at leadership by sector, so this was by revenue. If I looked at leadership by sector, the story is similar, right? So if start with aerospace industry and chemicals and so on, you see a very large number of companies where chemical engineers work, right? And they are quite, in a detailed way, they're involved. Of course, there are chemical engineering major part of investment in some other companies. So electronics companies like tech, what are called by the stock market as tech companies like Apple and so on, they also involve a large number of chemical engineers. Remember, when you have a mobile phone coming to you, it has a glass called Gorilla Glass on it, right? This glass, by the way, in my early part of my career, I was involved in some ways in development of this glass. And this is a very interesting glass, which is, of course, least breakable of all glasses. That is the chemical engineering innovation. So is the paint, so are the chips, wafers, everything that go in. So tech companies tend to involve a lot of chemies, actually, which is not what is popularly often understood. And if I look at the Indian situation, again, it's a similar story, right? Large majority of these are chemi companies, and some of them kind of linked, right? So Larsen and Toubro chairman until recently was a chemical engineer, in fact, from our department. And so it also does employ a lot of such people. But what I do want you to note as people who might be joining this profession or might be considering joining this profession is that corporate balance sheets are not the only signs of progress. See, they're an important part of society, right? I mean, finally, you want people to be wealthy and happy, and therefore you need to generate wealth, and therefore you need corporates. They're a very important part of any society or any political system. But it is not the only thing, because there are many problems which would not get addressed, which are important to mankind, but would not get addressed by corporates alone. So, for instance, things like drug discovery, right? Finally, at the final analysis, if you look at, say the COVID vaccines, for instance, so there were major corporates like Pfizer and Moderna and AstraZeneca and so on, and in India, Serum Institute and so on, who are actually involved in commercializing these products. But please understand, the technology and the science on which these vaccines were built was developed in academia over a very long period of time. And it's not that it happened overnight. Antiviral drugs that have been talked about were developed in research labs in academia. So what I'm basically trying to say is that there is a lot of work that also goes on outside the corporate space. Food processing, storage, water purification, air pollution monitoring, cleanup, global warming, alternate energy research. This is just naming a few. One important one I missed out here was electric mobility. But these are all areas in which different engineers work, but chemical engineers specifically involved in such things, right? So it's important that we understand how this all happened. So I already mentioned this in some way, and I will not belabor these points too much. But what I do want you to know that ancient civilizations were already talking about engineering chemistry, right? If you even look at some of our old scriptures, there was talk around this. They were successful to some extent, but obviously modern science, post-industrial age, really became, the hallmark of all engineering. Chemical engineering was no different. But before chemical engineering came along as a profession, there was this era of industrial chemistry, right? And some of this you might have even studied in your chemistry books. I would argue the most boring chapters of your class 10th, 11th, 12th books are possibly dedicated to industrial chemistry. Why I call it boring is that I think, at least the way I studied it, and I'm not very familiar with the modern, the new books that are there, but in general, they tend to be very descriptive, in the way they're taught in school. But the point is, it's actually very interesting. It's also a very interesting part of world history. any of you are a history buff or enthusiast, as to how technology blended into historical developments. But one thing which without getting into too many details, what I want you to note is that industrial growth in Europe actually was pushed by largely the textile industry. And the processing of textiles actually ended up happening because there was influx of raw materials from the colonies, like India, for instance, into England. This led to growth of new markets. And the industrial growth, it was soon realized, needed chemicals on large scale. So around the 17th and 18th century, 1700s, there was a lot of push in Europe to make chemicals at large scale. I think that scale is a very important point. Chemicals were made even before that, but they were not manufactured at large scale. And this large scale production, of course, happened with some chemicals like sulfuric acid initially. And this went through many different processes, some of which you might have heard about or read about, lead chamber method and various processes around that. I'm not going to get into details of it. That's not the purpose of this talk either. But I do want you to note that some of the inventions that were brought about at that time in the 18th century were actually ideas which are even used today. So if some of you listening to this are chemical engineers or studying chemical engineering right now, you would note that concepts like mass transfer, which is a very inherent part of all chemical engineering, did actually come about in the mid 19th century. The other big process that happened was the process around soda ash. Again, you might have heard about this, the Leblanc process. This also was a major kind of milestone, led to development of a lot of ideas which we now are part of chemical engineering in general. Solvay process was another, and I don't want to belabor that again. But what I do want you to note a little bit about this guy, George Davis. Right? So George Davis was an interesting person. He is credited largely with putting together the profession of chemical engineering. And the reason how he ended up doing that was that mid-19th century, working in England as what at that time was called an Alkali Inspector. Now, Alkali Inspector was a person who was supposed to go to various plants where they would make alkali. Alkali is, alkali, sodium carbonate, and so on, potassium hydroxide, sodium hydroxide. And at those days, there was no consciousness of environmental protection of any kind. So people would actually be polluting the environment by whatever waste they got. They would just throw it outside. So it's something like saying that you have a factory where you're making some chemical and whatever waste you have, you just throw it outside the factory and that's about it. No treatment, nothing. So in England, they came up with a law which said that, people are not allowed to pollute like that. And therefore, they invented this idea of having somebody called an Alkali Inspector. Now, Alkali Inspector, for obvious reasons, was a very lucrative profession because obviously there were a lot of violations in a license regime like that. And, they made some good money and not necessarily in the most holy ways. Anyhow, George Davis was an alkali inspector and he would visit a lot of alkali plants, charge sheet them, give them punishment, whatever. But one thing which he did observe is that he found that if you go to any plant, they're doing more or less the same thing. And some plants innovate better and do it better. There was no engineering in those days, right? So we're talking about 1860s. Engineering, mechanical engineering, civil engineering was just about starting. And this guy went about finding out what was really happening to the various alkali plants. And he said, well, by and large, if you look at all the plants, they all work on some common principles. And he put this together into a set of 12 lectures. And he called it a lectures on engineering of chemicals. And he delivered these lectures in 1887 to Manchester Technical School. Now, this is known as University of Manchester Institute of Science and Technology. You missed. Some of these lectures became very popular, right? And with that, he also coined a term called unit operations. Again, if some chemical engineers are watching this, you would know that these are standard things that are taught to you at undergraduate level. These lectures got so popular that there was word of this spread even in the United States. That there's this fellow called George Davis who has 12 very interesting lectures There was no internet, no online meetings, nothing of that kind. So George Davis was invited by MIT to deliver these lectures at MIT, and because they did not have a better name, so they just called it Course X, right? And the person who invited him to MIT was the then head of mechanical engineering, Lewis Norton. So MIT gave this Course X, right? And they became so popular that MIT decided to put together a new engineering discipline by this name called chemical engineering. And interestingly, this grew out of the chemistry department and the mechanical engineering department. The Course X, if you go onto the MIT website today, you will see that every course has a Roman numeral to it. But they've maintained X for chemical engineering. So now it's Course 10, but it still is the same notation. And then some other people followed. Again, not relevant to discuss it all here. But frankly, in Germany, then this was followed, and then in 1908, a society was formed in the United States called the American Institute of Chemical Engineers. Again, it exists till this day, and they became a professional society and said that no, we want to have this new profession. So the Course X became a template. Others copied it around the world, and both in Europe and United States in those times, and then eventually in India, also it came in the 1920s in Jadavpur University and in what is University Institute of Chemical Technology in University of Bombay. And then, of course, with time, various other things happened. I don't want to bore you with these details, but the point is that, by 1915 or so, this became a profession. A big change happened during the World Wars. So prior to World War I, the whole world was really running on coal, and shipping was all on steamships. And industrial chemistry had become a big deal. Germany had really expanded during the war and even before it. And industrial chemical manufacture became a big issue. And so chemical engineering really grew as a profession about 100 years back. Now, World War I led to a lot of problems in Europe. And so as a result of that, USA got cut off, at least for the first 3 years of World War I. In 1917, they also entered the war. But as a result of that, USA developed a big chemical industry of its own, right? And then the big thing which happened during the war and later was that the whole world was running on coal, but because of the invention of the internal combustion engine and the idea from Ford to commercialize automobiles at a major scale, a large scale. So before that, automobiles used to be only used by rich people. But the idea that everybody could, in principle, own a car or an automobile led to this requirement for massive expansion in oil, in the petroleum industry. And this indeed actually led to the requirement for petrol. And again, that caused a big growth in the chemical engineering industry. So again, let me skip some of the other details. But one thing which is of relevance even to this date is that post First World War, the entire Middle East was actually cut up by the Europeans in the Treaty of Versailles. And as a result of that, new nations got created like Iraq and Iran and so on. And with the result of that was that there was a big push towards oil refining, petroleum refining, and that led to the growth of the entire profession. Again, let me skip all of this. Second World War again saw a lot of growth of polymers, nylon. You probably know about it. And the other fact which happened is that Germany again got cut off from the rest of the world, and as a result of that, major innovations happened in Germany during Second World War, which we're using even till date. For instance, the synthesis of artificial petroleum, right? And so on, right? So many major things happen. Now let's come to what is more relevant for today. What are the major things of interest in at the present time, right? So what do chemical engineers of tomorrow likely to work on? Well, I'll come to a similar slide later. But I think the most important thing that you people might be working on are the demands for clean water and clean energy. And when I said clean energy, I mean not only renewable. I think what the events of the last 2 weeks have shown us, and it is not a one-off event, this actually happens all the time, that it is perhaps not feasible for most countries, China and India being the major ones, to get out of coal very easily. We will eventually get out of it, but I think that will take a good period of time, at least a couple of decades. Until then, we need to figure out ways of cleaning up our energy, right? And a lot of work is going on. I know in IIT Bombay, a lot of work is going on. In IIT Delhi, some work is going on. We are doing, there's a whole country, and for that matter, the whole world is moving in this direction of making existing energy cleaner. Renewable is, of course, a great thing, but it will take some time before everything can be replaced by renewable energy. As a result of that, carbon dioxide sequestration is a major thing, and we need to manage it. Electric mobility is going to come up, miniaturized electronics, wearables, electronics. I know you already have your Fitbits, but that's not really a wearable. When I say wearable, you have textiles with electronics, things of that sort. Wall hangings, which will second as an electronic, as a television, right? Or screens that you can actually roll up. These are things which are in the works. Please, there's no science fiction in this. The things in the works, you will see them in another 5 to 10 years, right? Personal and social security. Very briefly, I don't want to again belabor this point. I think we're going to run out of time shortly. But a major part of today's chemical industry is linked to the petroleum industry, right? And which means that this comes in different parts. There's an upstream part of the petroleum industry, which is drilling and exploration of oil. There's a downstream part of the petroleum industry, which is refining, right? So this is basically when you take petroleum and break it up into its individual components. And then there is transportation and midstream and the downstream part, which means after refining, you make chemicals out of it. Of course, a lot of our petroleum gets used as fuel, like natural gas or petrol or diesel and aviation turbine fuel and kerosene and so on. But a lot of that also gets used as petrochemicals, plastics, materials that you see around yourself. If you look around you, you'll probably find everything from the t-shirt you're wearing to the paint on your desk or the screen on your computer or your laptop or tablet screen or whatever, your printers, pencils, pens, everything that you see around, there's a large amount of polymers used in it. That's all coming from this downstream part of the petrochemicals industry. Right. So I think I've already described that. Let me skip these slides. An important point to appreciate is that the petroleum refining and this hydrocarbons industry is a big part of any economy, indeed in India as well, but it's really around the world. And part of what you might have seen in the geopolitics of the last 70 years, whether it is conflicts in Iran, conflicts in Iraq, things with Saudi Arabia, tensions between Russia and Europe, expansion into the South China Sea. It is in some ways all linked to this one product that you see on your screen, crude oil, right? And unfortunately or fortunately, energy is a very, very key part of our existence. So this drives many things, and in many ways, chemical engineers play a very key role in this entire industry. So one very famous chemical engineer whose name you might encounter in case you end up doing chemical engineering is Octave Levenspiel. He passed away recently, made many major contributions. These cartoons I got from him, and he basically had these cartoons where he refers to these as making friends with chemical processes. So essentially, chemical engineering is a lot about these processes, things we do. And he's basically saying, you must have the right process for the right thing. And it's essentially an idea of falling in love with these processes, right? So let's say you're making an omelette, right? A lot of chemical engineering is about making an omelette, put it in lighter terms. You need to have the right pan to make the right omelette, have the right temperature, you'll get your right omelette. Or if you are trying to barbecue a bull, right? You need the right furnace for it. And you have a little Texas cowboy who's trying to put a big buffalo on a barbecue grill and making a barbecue of it. If you don't do it right, then you might have an omelette on the furnace, which will not work. So chemical engineering actually tells you what is the right process to be done in the right way. And if you aren't particularly careful about things, again, you might try to barbecue a buffalo on a pan. This would not work either, right? So neither of these things would work. So engineering is a lot about the science, this physics, this fluid mechanics, a lot of heat transfer involved, a lot of thermodynamics involved. And then, of course, you have some chemistry also involved in this. It is perhaps a little bit more than other disciplines, but not completely. So basically to get your stir tank right. So now, last 5 minutes of what I was going to say is 11 past 2. So if you were to work as a chemical engineer, what would your career be like? Right? If you ask me this question, my honest answer would be, I don't know. Right? However, there is a little bit of experience that I've gathered over the years. And so if you were to push me on a spot and push me to hazard a guess, this is what I would say. What's going to happen in the next 10 to 20 years? Perhaps next 25 years. A big thing is going to be an increasing degree of automation of processes. Please understand that modern day chemical engineering is already all automated. There is no cooking like you might do at home, when you're making dal or khichdi or something like that. It is already all automated. But what it may not be, it is already working on artificial intelligence also. But what it may not be is that there are a lot, if you get into the depth of how chemical engineering processes work, if you know the difference between a linear equation and a quadratic equation, a nonlinear equation is something more than quadratic, has that many number of roots, and therefore it can have that many number of answers. There is a lot of nonlinearity that is now getting addressed with new techniques of artificial intelligence and machine learning. So I would guess that this is going to be even more. Going forward, we're going to see a lot more automation. The other big question, and when I say big, I want to highlight this. This is a big question around energy and sustainability, right? So I already mentioned this global warming and CO2 management, but again, I want to stress it again and again. Renewable energy is something we need for sure, no question about that. But the transition from the existing energy infrastructure to renewable energy is not going to be straightforward. It is not straightforward in developed countries. It is going to be even more complex in developing countries like ours. You cannot overnight switch off fossil fuels and say that, great, let's now have renewables all over. It's not going to happen. So you need a transition. You need a period where this change will happen. And depending on whom you ask, this change can be anywhere in the next 15 to 30 years. So by the time young professionals like you get into the workforce, this is going to be part of the main discourse. It's going to be the part of main discourse in engineering. It's going to be the part of the main discourse in banking, in investments, in stock markets. Everywhere you go, this is going to be a very main thing. So my point to you is, even if you are going into a career in finance, if you're going to a career in banking, you will need this knowledge. You really can't go without this knowledge. So that's important. Matters like air quality. If you're living in the northern part of India, like where I am right now, you will see this is a major issue in Delhi. And Bombay, it is less of an issue. It's quite bad in Bombay also, but it is less of an issue. In Delhi, it's a major issue. This is going to affect your quality of life in a big way. So addressing these challenges is going to be important. It is not just a political posturing anymore. It's affecting your lives, affecting the lives of your children. So this is important. Something needs to be addressed. Sustainable fuels, electric mobility too. So please understand, electric mobility is at the moment currently based on batteries, right? It's not the best way, but that's what it is at the moment. So the Tesla cars, which everybody's going gaga over, is really based on batteries. And battery is a chemical engineering device. Finally, your mobility is going to improve because of batteries, because of chemical engineering innovations. Of course, there's a whole different idea out there of using something called fuel cells. There are challenges there, but perhaps one might argue in some ways better than batteries, particularly if you're doing long distance transportation like trucks and so on. That's all chemical engineering. It's part of the curriculum in IIT Bombay, in IIT Delhi, in IIT Kanpur. Wherever you go, you probably learn about this. Health, of course, needless to say, in the times we live in, it's going to be a major thing. But I think what the COVID pandemic has taught all of us is that the dissemination of public health, very important, not restricted to cities alone, not restricted to rich or middle class people in cities alone, but having public health all around, distributed, going to the smallest of villages, has become an imperative. And this will require a lot of innovations. It's too healthcare as it stands now is too expensive to be disseminated everywhere. So this is going to be a big thing. Nutrition is a very big issue. So there's this whole new area of chemicals called nutraceuticals. I mentioned democratization of healthcare, medicines, vaccines, etc. That's obvious. A big thing that is going to happen is miniaturization in the chemical plant. So one of the pictures I showed in the beginning was all about large plants, but we might actually end up creating these miniature plants going into the future. Innovations like robotics are coming in, microfluidics, on-demand manufacturing of chemicals. So you make the chemical only when you need it. This is, a lot of robotics in this, lot of mechatronics in this. Please understand, disciplines are not hard boundaries. You really need to move on, and that's what's really happening also on the ground. Materials engineering, you might have heard of nanomaterials, also recyclable plastics. We know that plastics is a major issue nowadays, and so on. So these will also form important part of the profession going forward. And finally, this whole idea of integrating biology into engineering, into manufacturing. So there's biochemical engineering, which, depending on which IIT you are in, is a separate discipline from chemical, or it may be part of the chemical department. Most IITs have, I would not say most, but several of the IITs have this biomedical engineering department. They also have schools of biological sciences or departments of biological sciences. But the integration of biology into engineering is going to be a big thing. And that's for sure. It is already happening, but I think it's safe to say the next 20 years, it's going to be a big thing. As you know, MIT's even started a department of biological engineering, which really came out of their chemical engineering department. So I'd stop here. So thank you for your attention. I'm open for any questions, any comments, anybody has.
Thank you so much, Professor Shantanu, for such an insightful talk. It was really interesting to see the blend of history, the basics, and up to industrial level chemistry, not only for the students, the upcoming engineers, but also for me and myself as a chemical engineering student. And
great, thanks, Aditya. So any questions?
And also, most of the questions were covered by you during the speak. I'll take up some more of them. It's Neva. And okay. So one of these questions was, what are the opportunities of starting your own venture after studying chemical engineering?
Oh yeah, many actually, many. Please, let me not belabor that. In fact, this entire energy environment space is going to be a big thing, right? So there is a lot of startups already being conceived. I would say more in the Silicon Valley area. All startups, essentially, that's conducive for startups. But energy tech is going to be a very big thing, and the other important part is distributed energy tech. So batteries, fuel cells, one of the things that they bring up is distributing the energy. It's not, the current energy network is all centralized generation. So for instance, you have a thermal power plant and then you transmit electricity. But that's going to change in a big way. And so there is a lot of work to be done in tech startups dedicated to energy. That's happening. Also with healthcare, there are a lot of startups, pharmaceuticals, a lot of startups. So yes, a lot of entrepreneurship opportunities. And I think in many ways, the startup culture in the IITs, I can definitely speak for a couple of IITs I'm more familiar with, like IIT Delhi and IIT Bombay, IIT Kanpur. It is actually not too much into deep tech. And this is a problem. We like to celebrate our startups, but we really don't have too many deep tech startups. But I think that will change. It's going to change by circumstances. Partly also then the effort needs to be made. But in other parts of the world, deep tech startups are already a very big thing. So surely it's going to be a big thing.
Okay. And so this was another question, that what was the impact of pandemic and work from home culture can put in the career prospects of chemical engineering for 4 years from now?
I don't think it is any different from any other profession. There were challenges which I think companies have kind of made peace with. They've kind of found out ways. I don't think it's any different from any other profession. So please understand that a modern chemical engineering plant or a setup has very little human involvement. So most of it is remote actually. So I think 50 years back, you would actually go and open a valve and, change a setting and then something will flow. That it doesn't happen anymore. I mean, go into any, modern refinery in India for that matter. Refineries in India are at par with anywhere in the world. So it's nothing very different. But if you go to Panipat refinery or anything like you see, it's all remotely controlled. So I don't think it's any different from any other profession in that sense.
So I guess two people have also raised their hands. So now, can I unmute them?
Yeah, that you could take one of the questions.
Okay, fine. So I can see Aryan Shah first here, so I'll ask him to unmute.
Good evening, sir. Sorry, good afternoon, sir. My question is that the hot topic nowadays is the battery and the fuel cell. The research is going on. So it's not fully developed. It's in the works. So is it a big part in the curriculum in chemical engineering, or it's a very small aspect that is taught?
No. So see so let's handle it a little differently. So a fuel cell is a classical chemical reactor actually. And so is a battery. The big difference between the two is that the fuel cell has a fuel which is flowing in and out. Well, battery typically would have material that is already stored inside. The way these things work is based on principles which are actually taught or have been taught in chemical engineering curricula for a long time. The big difference that has happened. So, basically what do you need to study these things? You basically need a good amount of understanding of thermodynamics, which is really a follow-up of what you might already know and what you would learn in any engineering curriculum. It requires a good understanding of rates and physics, basically. And the big thing that is brought in by these two devices is good knowledge of electrochemistry. Right? That's an additional feature, which is not classically taught. But I think the curricula and the IITs for sure have already stepped up to that. And I can speak that we have in our department here in IIT Delhi, we have about 4 different elective courses in this field. Right. And I would guess that that's a similar situation in IIT Bombay or anywhere else. So for sure, that's part of the curriculum and students take that at undergraduate level. And a lot of PhD level research also going on, undergraduate research also going on. So yes, these are things which you should get into. And you're right, it is not fully developed. It's developed in the sense that yes, we have concepts that are there. And somebody's building cars out of it and we are all going gaga over it. But if you look at things like energy density, how effective is it? What is the efficiency level and so on? A lot is to be said about the IC engine. So IC engine has been around for 100 years plus and it's still going. So please understand that if you want to displace a technology as mature as that, it is not just about a Facebook post or a Twitter feed. If you want to replace the entire thing, the entire fleet of cars, it's going to require major innovation, and innovation in every aspect. That's all happening as we speak.
And the participants here look quite interested. So there was one more question that are there opportunities in pollution control as well?
Yeah, big ones. They're big opportunities. And in fact, I don't even think we've got any kind of solution particularly relevant to our country, right? So there are some solutions which are relevant to, say, the Los Angeles Valley, which had a similar problem like North India, maybe 3-4 decades back. Some of that has been taken care of, but in general, there's a replication model which is working largely, and that's not very useful. So, for instance, this crop burning issue is very local to India. It is not there in other parts of the world. And I don't think this has really been addressed. Of course, people are working on it, but there are issues around it. It's not that easy. So you must ask, why does a farmer burn crops? The main reason is that rice stock tends to have good amount of silica, right? And so I'm getting into the engineering of it. It has a good amount of silica. So therefore, chopping it quickly is not easy. And a typical farmer doesn't have in Punjab, for instance, does not have a very good period before decropping and a new cropping. So for him or her, for that matter, the easiest option is forget everything, just burn it.
Yeah.
That is because if you really try to cut, you can't cut that fast, right? And besides, even if I cut, what do I do with it? Because cows will not have that stock because it's too high in silica. So therefore, there's a reason why. So now you got to come up with a solution which will address this. Maybe you have better machinery, or maybe you have you can make something out of that crop or whatever. I mean, it has to be a sustainable solution. Just political posturing will not help. Right. So there's a lot to be done there.
All right. So I guess this was all these questions here. Okay.
So there's one question called, can artificial intelligence reduce the need for chemical engineers significantly? I don't think. My personal view is artificial intelligence is very essential and it will come into everything, but it will not reduce any engineering in my view. So AI is only an enabling tool. What it will end up doing is modify the discipline. Right? See, look, there was a period when people did a lot of research on how does flow happen in a pipe 100 years back. Now we take it for granted, right? The discipline has completely changed. So AI is here. It is here to change a lot of things, and it will. So shying away from it will not help, and nobody is shying away from it. Even if you want to shy away from it, nobody cares really. Business is going to move in a direction that it will, incorporate the new innovations. It will modify the profession, but then that modification is also part of your curriculum, right? So please understand that you get to do CS courses, you get to do course in mathematics while you are at any of the IITs, and whether you tell the undergrad students or not, they're going to go and do those things because it's important for them. So it is actually something which you have to do. You can't shy away from this. So for sure, this is important, but it will modify the profession like everything else. That's why I said these are some of the new things that are coming up. I listed those, right? AI was top of my list.
So, all right, students, there are many questions coming up. So there's another session lined up in chemical engineering at 6 p.m. So you can ask your questions there. So to Shantanu sir, a big thank you for taking out your precious time out of your busy schedule. And that was all from our side.
Thank you, Adit.
Thank you very much, sir, for joining us. And your session was truly very much insightful. And I must feel that the students must have got quite an overview. And I see Adit himself is from chemical, and he seems very much impressed with the talk. So thank you very much, sir, for accepting our invitation and giving out the talk over here.
Thank you, Nab. Thanks, Adit. And if you have any questions, you can if you can consolidate and send me something, I can also always respond on email, which you can possibly share.
Sure, so we'll work something out that.
Okay, great. Thank you.